What you're watching is a visualization of one of the hardest problems in modern aerospace engineering. Air flowing at Mach 5 moves so fast that a cubic centimeter stays inside a combustion chamber for roughly 1 millisecond. Trying to light fuel in that hyper-turbulent window and keep it lit is like trying to strike a match in a hurricane. When you hear about hypersonic technology in the news, you are usually hearing about two entirely different concepts smashed together. There are boost glide vehicles, which are already fully operational, and then there is the highly experimental frontier of air-breathing hypersonics. Boost glide systems are relatively straightforward. A traditional rocket punches them up to hypersonic speeds, and they simply glide back to Earth along a guided ballistic trajectory. They do not have engines of their own, and they don't breathe air. Because unpowered falling bodies are a solved engineering problem, pretending they are the same thing as sustained engine-driven flight gives a false sense of maturity to actual air-breathing hypersonic development. To understand why air-breathing hypersonics are so difficult, look at a standard passenger jet. A conventional turbojet relies on rotating compressor blades to squeeze incoming air. But push past Mach 3.5 and slowing that supersonic intake air down to subsonic speeds generates stagnation temperatures high enough to melt those moving metal blades. The initial solution engineers developed was simply removing the moving parts. Instead of a spinning compressor, a ramjet uses the sheer forward speed of the aircraft's ram effect to force air into the engine, slowing it to subsonic speeds for combustion. That works beautifully up to about Mach 5. But above that speed, slamming supersonic intake air down to subsonic velocities creates so much pressure and heat that the air molecules actually dissociate, breaking apart before the fuel can even burn. This diagram shows the core difference across these three engine types. To survive past Mach 5, the air inside the engine cannot slow down. It has to stay completely supersonic. That dictates the final architecture, the supersonic combustion ramjet, or scramjet. Notice how the scramjet compresses the flow. Instead of turbine blades, it relies purely on the sharp angles of the intake and the vehicle's own four-body shockwave riding off the nose to squeeze the air, all while keeping the velocity firmly above Mach 1. Flying at Mach 5 means abandoning mechanical compression entirely. The shape of the vehicle itself becomes the engine. This is what testing that concept looks like in reality. This heavy, highly instrumented rectangular module is a scramjet combustor, mounted inside a hypersonic wind tunnel cell to simulate extreme altitude and speed. The engineer here is seating a metal fuel injection strut. During a run, this precise piece of hardware must evenly distribute fuel into an airstream, tearing past at over 2,000 meters per second. To keep that aggressive crossflow from immediately blowing the flame out, the internal geometry uses cavity flame holders, small recessed pockets that create localized, low-speed eddies where the flame can safely anchor itself. Liquid hydrogen is often the preferred fuel for these tests because its high heat capacity makes it an excellent coolant. But hydrogen is incredibly bulky. Its low volumetric density requires massive tanks, making it very difficult to package into a compact airframe. Everything inside this combustor is designed to manipulate time. The geometry forces the fuel to mix, ignite, and burn completely before that 1 millisecond window of residence time expires. When a ground test initiates, the sequence is violent. High-pressure gas manifolds snap open, flooding the test section with air to match the dynamic pressure of high Mach flight. This image captures the physical proof of success. That brilliant exhaust stream shows sustained supersonic combustion, complete with a steady chain of shock diamond structures locked directly into the plume. Many designs operate in a dual mode, flying as a standard subsonic combustion ramjet at lower speeds before switching to a scramjet. But crossing that threshold creates unsteady pressure spikes that can easily travel back up the intake and extinguish the flame. Engineers monitor pressure traces closely during a run. A flat, steady line on the graph proves the flame is holding its ground against the destructive flow dynamics. Wind tunnels are excellent for proving dynamic pressure and basic geometry, but because no ground facility can perfectly replicate the complex, real gas chemistry of the upper atmosphere, engineers still have to put the hardware on an actual aircraft to know for sure. Internal combustion is only half the battle. As a vehicle pushes through the atmosphere, the friction and compression of the air generate extreme heat, and that aerodynamic heating scales roughly as the square of the vehicle's Mach number. Look at the severe discoloration on this component. At Mach 5 to 8, the leading edges of the aircraft hit stagnation temperatures between 1500 and 3000 degrees Celsius. Standard aerospace metals soften, oxidize, and ablate away well before reaching those numbers. Surviving that environment requires exotic materials. Leading edges are capped with ultra-high temperature ceramics, like hafnium diboride, while the combustor walls use active regenerative cooling, routing the cold fuel itself through the metal skin to absorb heat before injection. The engine acts as a furnace on the inside, while the atmosphere acts as a blowtorch on the outside. The vehicle has to survive both at the exact same time. Bridging the gap between theoretical models and physical survival requires an exact match between the original blueprints and the final machined hardware, down to the millimeter spacing of the injection ports. This photograph shows how that hardware actually gets to the sky. Private companies like Stratolaunch are deploying reusable hypersonic testbeds, dropping these small, rocket-accelerated vehicles from heavy carrier aircraft to gather clean aerodynamic data in the real world. The ultimate goal for runway-capable flight is a turbine-based combined cycle engine, or TBCC. This architecture merges a traditional turbofan with a high-speed ramjet and scramjet into one continuous flow path. Achieving reliable, maneuverable hypersonic flight relies entirely on continuous, iterative physical testing, separating serious aerospace engineering from conceptual hype. If you want to dive deeper into the raw propulsion physics, material sciences, and the open engineering challenges discussed here, this is the link. Head over to Pro-Ready Engineer to explore the data and mechanics actively solving the hardest combustion problems in aerospace.